This recording is for the second half of Module 10 in Physics, and I want to start by putting up for you just the formulas that we need to worry about in this chapter so that you can have these on your card. These are the equations that you will be required to know how to use for completing Module 10. I haven't gotten to all of these yet, and some of them, for example, this one, you should remember from previous modules, and we'll be applying it in the mass spring applications that we are dealing with in Module 10. Okay, so I said last time that we would start by doing some of the on your own. So I said we'd start with on your own 10.4, and then we would do on your own 10.5. So let's do 10.4. On your own 10.4 gives us a 351 gram mass, and so I'm going to go ahead and change that to kilograms by dividing by 1,000. And it tells us that it's displaced from equilibrium. When it is displaced from equilibrium, it stretches 12.1 centimeters. So I'm going to go ahead and write that as meters, 0.121 meters. And then it says if the mass is pulled down 5.1 centimeters from this new equilibrium position and then is released, what will the period be? So we're going to pull it down from the equilibrium position, which it settled at here. We're going to pull it down 5.1 centimeters, or that is equal to 0.051 meters. Okay. So the first thing that you should recognize in this equation is that this value is the amplitude. Okay, it's the displacement from equilibrium. Okay, so when we hung the mass on it displaced this much. That was the new equilibrium, and then we pulled it down farther. So this would be the amplitude, and we are asked to find what the period will be. Well, we know that for a mass spring system, the period is 2 pi times the mass divided by k. Okay, so what we said previously was that the displacement from equilibrium, or the amplitude, does not figure into the period. It doesn't matter how far you pull that mass down, the period is going to be the same. The two things that influence or determine the period are the mass and the constant, the equilibrium constant, and not amplitude. Amplitude does not factor in determining the period. Okay, so the first thing we need to do then is we know the mass, but we don't know K. However, we can figure out K because we know that F is equal to negative K times delta X. And we know that this F is the restoring force. It's the force with which the spring will pull up to counteract gravity. So if we determine the weight, then we can determine this restoring force and then use that information to determine K. So the weight is mass times gravity. So weight is going to be equal to 0.351 kilograms times 9.8 meters per second squared. So the weight is 3.4 newtons. And we're going to assign that a negative value because it's in the downward direction. And so if the restoring force is always opposite that, opposite the direction of the displacement. So the restoring force then will be equal to 3.4 newtons. Okay, so now we can use that value to, in this equation, to determine K. Okay, so let me erase this. And we'll go back up here. So now we have that 3.4 newtons equals negative K times delta X. Well, what is delta X? Well, delta X is the amount that the object that the mass causes the object to be displaced from equilibrium. And again, it's going to be in a negative direction because it is going downward. Okay, so this would be 0.121 meters. Okay, so we're going to take 3.4 newtons divided by negative 0.121 meters. So we got our units Newton meters, and that's going to equal to negative K. So K will just be the positive sign. So 3.4 newtons divided by negative 0.121 newtons is negative 28.1. So 28.1 newtons over meters is equal to K. And we can have two significant figures. So this would just be 28 newtons over meters. Okay, so that's K. So now with that value, we can plug that into our equation for period. So let's do that. Okay, so T is equal to 2 times pi square root of the mass, 0.351 kilograms, divided by K, which we just said was 28 newtons over meters. I'm going to change this newton to a kilogram meter over second squared. Okay, because that's what a newton is. So you can see the kilograms are going to cancel, the meters are going to cancel. You're left with seconds squared. Take the square root of that to get seconds. So if we do this division and square root and multiply by 2 and multiply by pi, then what we end up with is 0.70 seconds. Okay, so the amount of time that it will take that mass to go up and down is equal to 0.70 seconds. That is the period. Okay, then on your own 10.5 ask us what if instead of pulling the mass down 5.1 centimeters, we instead pulled that mass 10.2 centimeters away from the new equilibrium position? Well, we don't need to do any math on this one because we know, so these are amplitude values, and we know that the amplitude in a mass spring system does not have any bearing on the period. So the answer is that the period would be the same as it was in the previous example. It would be 0.70 seconds, okay, because amplitude has no bearing on the period. Okay, so those are the two problems that I said we would start with. Okay, now we're going to switch gears a little bit, and we're going to start talking about how energy relates to a mass spring system. And let's start talking about potential energy. So when you stretch or compress a spring, we've already said that when you do that, there is a restoring force that tries to get it back to equilibrium. And that because you've applied a force, that force is capable of doing work. And anything that is capable of doing work has potential energy. So when you pulled the spring down, it had potential energy and it was ready to do work. When you release that spring, then the potential energy gets converted to kinetic energy. And as more potential energy gets converted to kinetic energy, then the mass is going to move faster and faster, and it'll keep doing that until it reaches its equilibrium position. And we already said that at the equilibrium position, it would be going at its maximum velocity, which means that at that point it would be all kinetic energy and no potential energy, because all the potential energy at that point has been converted to kinetic energy. But the mass still has a lot of kinetic energy, so it's going to continue to move. And what it's going to do now, it's going to compress the spring. And in order to do that, then what you're doing is you're converting that kinetic energy back into potential energy. So when all the potential energy is converted back into potential energy, then the spring will stop, or the mass will stop. So now again, we have all that potential energy, and so then the mass is going to start moving in the opposite direction. So think about that and try to visualize that mass moving up and down and what's happening to potential and kinetic energy as it does that. We can draw this with a graph. So on the y-axis, I'm going to put energy in joules. And on the x-axis, we're going to put the displacement from equilibrium. And so right in the middle, we'll call this 0. So in the middle, which would be when the mass is at its equilibrium position. So if we were to draw a graph, one for potential energy and one for kinetic energy. So let's do blue as the potential energy. And what you're going to see happening is you're going to So that is the potential energy. And then red would look the exact opposite. So at the 0 point, so it would the graph would look like this. So what does this tell you? Well, it tells us that at the equilibrium position, all of the energy is kinetic energy. So this is, the red is kinetic, and the blue is potential. So at the equilibrium position here, all of the energy is kinetic energy, and none of it is potential energy. But if we look at the extremes here, where the spring has been compressed, here where it has been stretched, when the spring is at its amplitudes, it's all potential energy and no kinetic energy. So kinetic energy at that point is 0. Kinetic energy at this point is 0. And then, as that spring moves through the length, some of that potential energy gets converted to kinetic energy, so that at the 0 point, at the equilibrium position, it is all kinetic energy. Okay, so that figure is in your book. So you can look at that and again think about that. Try to visualize that happening with a mass spring system. So, so what we said is that at its amplitude, a mass spring system has no kinetic energy, and is all potential energy. So at amplitude, it's all potential energy, no kinetic energy. And we said that at equilibrium, it is all kinetic energy and no potential energy. So all of the potential energy has been converted to potential energy at the equilibrium position. And since it's all kinetic energy, this would tell us that this would also be at its maximum velocity when it is at equilibrium. And we talked about that last week. Okay, so this next formula, we're not going to go through the derivation of it because it's more complicated than this course allows us to do, or for your understanding of physics to allow us to do. But that formula is that potential energy is equal to 1/2 K times delta X squared. Okay, and so what this equation tells us is that the potential energy of the spring depends on the equilibrium constant of the spring, so it depends on it depends on the strength of the spring, and it also depends on the displacement from equilibrium. And that should make sense because the farther you displace that spring from equilibrium, the more potential energy it is going to have. Okay, and then let me remind you also that from previously we know that kinetic energy is equal to 1/2 times the mass times velocity squared. Okay, and then we also know that energy cannot be created or destroyed, so it has to it can only be converted from one form to another, and we're looking at how it can be converted from potential energy to kinetic energy. Well, if we think about the fact that at its maximum velocity, so when when the spring is displaced to its amplitude, its kinetic energy and its maximum velocity is equal to 0. Okay, and so then what that tells us then is that all of at amplitude, all of the energy is potential energy, and so we can, since all the energy is potential energy, we can say that that is equal to this 1/2 k, but instead of putting in delta x, we're going to put the amplitude and square that. Okay, so when the potential energy is equal to 0, when the kinetic energy is equal to 0, which we said happens at amplitude, then all of the energy would be potential energy. So all we've done then is said that at amplitude, the kinetic energy plus potential energy is going to equal to 1/2 times k, and then we just substituted delta x for a squared. Okay, so think through that and make sure that you understand the reasoning there behind that. Okay, so let's start by looking at On Your Own 10.6. Okay, so in On Your Own 10.6, the question asks, how much work is required to stretch a strong spring? So we're told that K is equal to 3,412 Newton over meters, and that we're going to stretch it 34.5 centimeters. And we want to know how much work is required to do that. So I'm going to go ahead and convert this to meters, so our units are consistent. Okay, so when it's asking how much work is required to stretch it, what it's really asking for is the potential energy. And we know that potential energy is equal to K times delta x squared. So that's going to be equal to 3,412 newtons over meters. And then delta x was 0.345 meters, and we're going to square that. Okay, so I'm going to go ahead and instead of this newtons, I'm going to put in kilogram meters over second squared. A newton is a kilogram meter over second squared. Okay, so we will end up with a Newton meter. So here's the Newton, and one of these will cancel. So you're going to end up with a Newton meter, which is the proper unit for energy. And if we do this math, we will get 203 Newton meters, or 203 joules. Okay, so 10.6 is just a simple, straightforward application of the formula for potential energy applied to a mass spring system. Okay, now we are going to look at On Your Own 10.7. And On Your Own 10.7, let's write down what we are given. So we have a 61.2 kilogram mass, and it is placed on a spring and set into harmonic motion, and we are going to pull it 23.1 centimeters from its equilibrium position. So I'm going to go ahead and convert that to meters. So it's 0.231 meters from its equilibrium position. And we are told that the maximum speed is 3.4 meters per second. And then we are asked to figure out what is K. Okay, what is K? Okay, so we know that the kinetic energy, so because we're talking about this mass at its maximum velocity, we know that we're dealing with its kinetic energy. So kinetic energy is equal to 1/2 times the mass times the velocity squared. So we can determine the kinetic energy with the information that we have. 1/2 times 61.2 kilograms, and then square the velocity. 3.4 meters per second times 3.4 meters per second, so that the kinetic energy is equal to 354 joules. So a Newton, this is going to come out to a Newton meter, which is a joule, but we can only have two significant figures, so this is going to be 350 joules. Okay, so that is the kinetic energy. So what does that tell us? Well, we know that potential energy plus kinetic energy so we know that kinetic energy plus potential energy is equal to 1/2 times K, and then the amplitude squared. Okay, so since we are at maximum velocity, what is the potential energy at maximum velocity? Well, it's 0. Okay, so that then tells us that kinetic energy plus 0 is equal to 1/2 times Ka squared. And we just figured out that kinetic energy is 350 joules. So 350 joules plus 0 is equal to 1/2 times Ka squared. So now all we have to do is solve for K. So 350 joules. So 350 Newton meters divided by 1/2 and divided by the amplitude, which is displacement from equilibrium. Okay, so meters are going to cancel here. We'll be left with a Newton over a meter, and that's what K is. So then what we end up with is that K is equal to 1.3 times 10 to the 4th newtons over meters. And so that's a pretty strong spring there. So we started out, since we knew the maximum velocity, we knew that we were talking about kinetic energy. So we figured out kinetic energy, and at maximum velocity, potential energy is going to be 0. And then we know that the kinetic energy plus the potential energy has to be equal to this, and then we just solve for K. Okay, so that is on your own 10.7. Let's look at on your own 10.8. Okay, on your own 10.8, we are given that we have a 54 gram mass. So I'm going to go ahead and just convert that to kilograms. And we are told that the spring constant is 15 newtons over meters. And if it is displaced 5 centimeters from its equilibrium position, so we're going to displace it 5 centimeters, which is 0.05 meters from its equilibrium position. So what is that? Well, if it's the displacement from equilibrium position is its amplitude, and it says how fast will it be traveling when it is 2.5 centimeters or 0.025 meters from equilibrium. Okay, so what's this equal to? Well, this is equal to its displacement away from equilibrium. So that would be equal to delta x. Okay, so the amplitude is how far is it pulled down. The displacement from equilibrium would be the 2.5 centimeters. Okay, so what are we asked to find? We want to know how fast is it traveling at this displacement. So we are interested in the velocity. Okay, so how can we get there with the equations that we have? Let me put up that 0.025 meters and 0.05 meters. Okay, so this is A, and this is delta x. Okay, so using the equations that we have, so when it is at its when it's at its when it is at its displacement of 0.025 meters, we can figure out what its potential energy is at that point, okay? Because we know that potential energy is equal to 1/2 K times delta x squared. Okay, so we'll just plug in here 1/2 times K, which is 15 newtons over meters, and then the delta x squared will be 0.025 meters squared. Okay, so the potential energy when it is displaced this far from equilibrium comes out to 0.0047 joules. Okay, so that is the potential energy. Well, then what can we do with that? Well, we know that the kinetic energy plus the potential energy is equal to 1/2 K A squared. Okay, so can we use that then to determine the kinetic energy? Yes, because we know everything except the kinetic energy. So then I'm going to take kinetic energy plus the potential energy that we calculated, which was 0.0047 joules, equals 1/2 times K, 15 newtons over meters, times A squared, okay, so now I'll do this multiplication, subtract this from both sides, so we'll do all this, and then we'll subtract the 0.0047 joules. And when we do that, we will get that the kinetic energy is equal to 0.014 joules. Okay, so now we know the potential energy, we know the kinetic energy. what we were asked to find was the maximum velocity. Well, now that we know the kinetic energy, we can use our formula for kinetic energy to get the maximum velocity. Okay, so we said that kinetic energy is equal to 1/2 mass times velocity squared. So now we just plug in the mass, plug in that kinetic energy, and we can solve for v squared. So kinetic energy divided by 1/2 and divided by the mass will equal v squared. So if we take the square root of that, that will give us v. So if we do that math, so let's plug in the value for, well, instead of erasing it, I'll just put them in here. So the kinetic energy was 0.014 joules, and we're going to divide that by 1/2 and divide by the mass, which was 0.054 kilograms. So do the division, divide, then take the square root of that. That's going to be equal to v. And what you should get is that v equals 0.72 meters over seconds. Okay, so this was a case where we first had to determine potential energy. Then we set the potential energy equal to 1/2 k a squared to determine kinetic energy. And then once we know kinetic energy, then we can use our kinetic energy formula to determine the velocity. Okay, so that is example, that is on your own 10.8. Okay, the next thing we are going to talk about then is how does a pendulum relate to simple harmonic motion? Okay, so if we have an object that is hanging straight down like this, we know that the tension on the string will be equal and opposite to the force of gravity, right? So the force of gravity is going to pull this down. There's going to be a tension on the spring that is going to be equal and opposite to that. So that in this situation, the net force is equal to 0. Because we have T pulling up this way, we have weight due to gravity pulling down that way, and they are equal and opposite. Okay, so then what happens if, what if we displace that object? So now, instead of it hanging down here, what if we displace that object to hang out here? Okay, so this will be the tension on the spring, and weight will be here, right? And you know from before that we can separate that weight vector into two components, right? So we can separate the weight vector into its x component, which is w times the cosine of the angle, and we can the other component would be w times the sine of the angle. This is in your book, and it's drawn much better than I just drew it. So you can see that the tension and w cosine angle are going to cancel each other out. But there's nothing opposing this vector, right? Nothing opposing that vector. So that means that when you displace this object, because there's nothing opposing this angle or this vector here, then that means that the object is going to move back toward the equilibrium position. So that when it reaches its equilibrium position, the force is going to be 0, but it's still going to have velocity. So it's going to move past the equilibrium position in the other direction. So it's going to move, that object's going to move here. And then gravity is going to start pulling on it again, and it's going to pull it back to its equilibrium position so that it's going to slow down and its speed is going to be 0 here. But then gravity is going to pull it back the other way, so you're going to get this pendulum motion back and forth. So W sine angle is always going to point toward the equilibrium point. So it's always pointing back towards equilibrium. You can see that here. Okay, it's all, if this is equilibrium, it's always going to be pointing toward equilibrium. So if it's always pointing back to equilibrium, what do we call that? Well, we call that the restoring force. You may or may not have been exposed to this in your math, but what we know about a restoring force is that if the angle is small enough, and if we use radians instead of degrees, which we typically use, then the restoring force is equal to the weight times the angle. And this is true as long as the angle is about no more than like 20 degrees. As long as the displacement away from equilibrium is small, then the restoring force will just equal to the weight times the angle. So I don't expect you to follow this derivation, but the S is used would be the length of the arc of the pendulum, and R is equal to the radius times the angle. So S is basically the displacement from equilibrium, and R is the length of the string. Okay, so then what we have is that delta X is equal to the length times the angle. And so basically what we see then is that the restoring force is proportional to the displacement from equilibrium. So we saw that before, right? So if the restoring force is proportional to the displacement from equilibrium, and if the angle is small enough, and we define small enough as less, no more than about 20 degrees, then a pendulum is an example of simple harmonic motion. So we already know that the period in simple harmonic motion, the period does not depend on the displacement from equilibrium. So delta X doesn't matter as long as the angle is less than 20. So the period is the same for angle. If the angle is from 0 to 20 degrees, then the displacement from equilibrium doesn't matter. And that is what allows us to tell time from a pendulum. So it doesn't matter how far the pendulum is pulled from equilibrium, it doesn't affect the period. So it doesn't affect the time. So then what does affect it? Well, the only thing that affects it then is the length of the string that the pendulum is suspended from and gravity. So acceleration due to gravity and the length of the string is the only thing that determines the period, not the how far the object is displaced from equilibrium. So we don't need to know delta X. We don't need to know how far it's displaced from equilibrium. We just know need to know the length of the spring, and the longer the length of the string, then the longer will be the period. Okay, so let's apply this then to some examples. Let's do on your own 10.9. Okay, on your own 10.9, we are asked what is the period of a pendulum whose length is 2.5 feet. Okay, and we know that period is equal to 2 times pi, and then it's the length divided by gravity. Okay, so we are given the length, so 2 times pi, the square root of the length is 2.5 feet. And since we're dealing with feet here, then for gravity, we will use 32 feet per second squared. Right, you could have, it would have been more work, but you could have converted this to meters and then used 9.8, but it's simpler to just keep it in English units. So then if we do this math, take the square root and multiply 2 times pi, what you get is that you'll get 1.76 seconds, but we can only have 2 significant figures. So t is equal to 1.8 seconds. Okay, so that is the amount of time. We have a pendulum. The 1.8 seconds is how long does it take to go over one way and back to the other. So how long does it take to make one full movement from equilibrium in each direction. Okay, so that is on your own 10.9. Let's look at on your own 10.2 or 10.10. So in that one, we are given the period. So we're told that t is equal to 0.45 seconds. And we are asked what is length. Okay, so t is equal to 2 times pi divided by the length times gravity. Okay, so we need to solve for L so that we would get rid of the square root by multiplying everything by squaring everything. So then it would be t squared is equal to 4 pi squared times L over G. Okay, so then we just need to solve for L. So we'll multiply both sides times G and divide both sides by 4 pi squared. Okay, so G times T squared divided by 4 pi squared is going to equal L. So G is 9.8 meters per second squared. Times t squared, and that was 0.45 seconds. And we're going to square that. And then we're going to divide by 4 and by pi by pi. And that will equal L. So if you do all of that math, what you should get is that L is equal to 0.05 meters, 0.050 meters with 2 significant figures, or if you want to convert that back to centimeters, which we started with, it would be 5.0 centimeters. Okay, so you just need to remember that in simple harmonic motion, the displacement from equilibrium does not influence the period. So Doesn't matter how far you pull the object away from equilibrium in a pendulum, it will not influence the period. The only thing that influences period is the length of the string from which the object is hanging and gravity. So it will obviously be different on different planets depending on gravity, but we'll deal mostly with Earth. If I want to give you a problem for another planet, I will give you what the acceleration due to gravity is. Okay, so that finishes up Module 10 for physics. And in another video, I will work all the problems for you for the practice problems for Module 10.